Thank you, Chairperson, for the introduction. I'm Rinsuke Yamada from University of Tokyo. Today, I will talk about Nernst effect of high mobility wire electrons in neodymium silicon enhanced by a film surface nesting instability. And this talk is a little bit different from the previous talks. And in this talk, I will focus on the thermoelectric effects, which converts the temperature gradient into a useful electricity. And let me start with the introduction. So, the thermoelectric effects convert the temperature gradient into the useful electricity. And there are two types of thermoelectric effects. One is the Seebeck effect, the other is the Nernst effect. In Seebeck effect, we can get the voltage in parallel to the temperature gradient. On the other hand, we can obtain the voltage in perpendicular to the temperature gradient if we utilize the Nernst effect. So if we consider the practical use, if we want to use the Seebeck effect, we need to make a complex structure. On the other hand, if we utilize the Nernst effect, because the Nernst voltage is generated perpendicular to the temperature gradient, a much simpler device structure is available. So that's why people are now starting interested in this transverse thermoelectric effect called Nernst effect. But in this talk, I want to utilize this Nernst effect in different perspective. So if we use the simplest model with single carrier case, the Seebeck effect can be written in this formula, composed of density of state term and the relaxation time effect. And usually people focus on the former term, which is corresponds to the inverse of the film velocity. And people investigated the materials with low carrier density to enhance the Seebeck effect. However, here, in order to expand the material research field, I want to focus on the latter term, that is the thermoelectric effects caused by the relaxation time. So if we focus on the Nernst effect, this first term of density of state term disappears if we think of the most simplest case. And only this relaxation term remains. So we can say that Nernst effect would be a good measure to explore this possible new thermoelectric effects caused by this tau effect. So there's several previous reports on this relaxation time contribution to the Seebeck or Nernst effect. One example is the fluctuation of the topological magnetic textures can create such tau effect. And also there are other work on the semiconductors. However, there has been no quantitative research on this relaxation time contribution. So in this work, we focused on the magnetic wire semimetal neodymium silicon. This material has a tetragonal crystal structure as shown here, and it breaks the inversion symmetry, resulting in the topological wire symmetric state in the band structure. And it enables us to observe the high mobility wire fermions in the transport properties. If we turn our attention to the magnetic properties, the neodymium silicon shows the ferrimagnetic ordering at a low temperature. And this is the magnetic structure. The Q vector is along 110 direction of the tetragonal crystal structure. So if we look at the neodymium atoms along the 110 direction, spin up, down, down state is realized in this compound. And the characteristics of this compound can be seen in the Brillouin zone. Due to this periodic modulation of the magnetic structure in real space, the Brillouin zone is folded, as shown in this figure. And interestingly, the distance between the wire points will agree with the Q vector of this magnetic ordering in this compound. Therefore, we can expect that these wire points would be significantly affected by this magnetic ordering. So in this study, we explored the possible new thermoelectric effect induced by the magnetic nesting instability in magnetic wire semi-metal neodymium aluminum silicide. So here is a method. We synthesize a single crystalline sample of neodymium aluminum silicon and then measure the resistivity and the thermoelectric properties. And then we adapted the semi-classical approach by using the two carrier fitting to the Nernst effect, and then we quantitatively analyzed the relaxation time contribution. Then let me start with the result on electrical transport, that is Hall effect. So here I show the Hall conductivity at different temperatures. We fitted this field dependence of the Hall conductivity by using the two carrier model, assuming the two Hall pockets. And the extracted parameters are shown on the right. By comparing with the result of the quantum oscillations, we identify that these two Hall pockets correspond to the quadratic gamma pocket and also the wild beta pocket with linear boundary dispersion. And after establishing that the electric transport can be described by these parallel conduction of these two Hall pockets, we want to move on to the thermoelectric effects. So here I'm showing the raw data of the Nernst effect of neodymium aluminum silicon at high temperature and low temperature. When we decrease the temperature below 100 Kelvin, the Nernst effect is enhanced down to 12 Kelvin. However, if we further lower the temperature, the Nernst effect decreases down to 2 Kelvin. On the right, I summarize the temperature dependence of the Nernst effect at 3 Tesla, and we found that the Nernst effect is enhanced just above the nail temperature, maximizing around the 12 Kelvin. And from here, I'd like to discuss the origin of this enhancement of the Nernst effect. So in order to analyze this effect, we developed a way to analyze the Nernst effect by using the two carrier model. And here I assumed the parallel conduction of the quadratic gamma pocket and the beta pocket with linear dispersion. And here I'm showing the result of the fitting by using these two carriers, and we got a well fitting to the experimental observation. And from this fitting, we can extract the band parameters such as effective mass or the film velocity. And here I plotted the extracted mass and film velocity at different temperatures. And we found that these extracted parameters shows a good agreement with the quantum oscillations analysis. And this result supports that our analysis is quantitatively correct. And furthermore, we extended this analysis down to the lowest temperature. So here I am firstly showing the result at the lowest temperature of 2 Kelvin. You can see that at 2 Kelvin, we can also explain the experimental observation only by assuming the two carrier contribution of gamma and beta pocket. However, in the intermediate temperature regime, we found that there is a large discrepancy between the experimental observation and the two carrier model simulation. And we'd like to here discuss the origin of this additional component in the Nernst effect. Firstly, one possibility is the anomalous Nernst effect caused by the magnetic ordering. However, we excluded this possibility because this additional term disappears at the lowest temperature of 2 Kelvin. Then we attributed this additional component to the relaxation time effect. Here I derived the field dependence for this relaxation time effect by using the semi-classical model. And then assuming that this contribution is coming from the wire sigma pocket, that is would be significantly affected by the magnetic ordering. And then we fitted the field dependence of the additional component as shown here. And we found that we can nicely explain the experimental result by using this tau effect. And then from this fitting, we can quantitatively estimate this quantity of energy derivative of scattering time. And this is plotted as a function of temperature here. And you can see that this relaxation time effect is enhanced just above the nail temperature and maximizing around the 12 Kelvin, which is very similar to the temperature dependence of the Nernst effect. Then we concluded that the enhanced Nernst signal is originating from the magnetic fluctuation of this wild sigma pocket. Then lastly, let me in more detail explain the origin of this Nernst effect. So here we propose that the enhanced or additional Nernst effect is coming from the energy derivative of scattering time. And we can decompose this term into the inverse of the film velocity multiplied by the momentum dependence of the scattering time. So we can say that this term would be enhanced if there is a large momentum dependence in the scattering time. And we think that it happens in our compound. Here I'm showing the contour lines of the scattering time. And this red one is a film surface. And this yellow line indicates the nesting condition of this in this compound generated by the magnetic ordering indicated by this Q vector. So if we consider the part of the film surface close to the nesting condition, this part would be significantly affected by the band folding of the magnetic ordering. On the other hand, if we go away from this nesting condition, such reconstruction would be less significant. So such things would create the large momentum dependence of the scattering time. And here we'd like to propose a new way to enhance the Nernst effect by using the band folding nature by using the magnetic ordering. So here's a summary of my talk. In this study, we studied the Nernst effect in magnetic wire-thin metal neodymium aluminum silicon, and we demonstrated the quantitative analysis using the semi-classical model to the Nernst effect. And then we extracted the relaxation time effect and proposed a new thermoelectric effect by using the band folding nature of the band structure. Thank you for your attention.
Thank you for the talk, Dr. Yamada. Let's move on to the question time. Does anyone have question, comment? Okay, please ask.
Hello, Yamada-san. Thank you very much for your talk. It was quite nice. I just have a question on your Nernst effect signal. So for high B field values, there's quite a large periodic signal. I'm just curious about the origin of that periodic structure.
Yes, that's coming from quantum oscillations.
Okay.
Yes. Yeah.
Yes. Those. Yes. Yes. Thank you.
Yes. By using this oscillation, yeah, I estimated this dotted line. Yeah. Quantum oscillation. Yeah.
I see. Okay. Thank you.